A3 Work, Energy and Power. This topic is for standard level and higher level students, and actually it's one of my favourites. The concepts are relatively easy, but the exams tend to score highly for them. A lot of maths involved, but you can do it, I'm sure you can. We'll work through the 9 learning objectives shown on the screen right now. Use your revision note template and write down what I tell you to write down, and use those knowledge questions to test your knowledge. We're going to start A3 Work, Energy and Power with a little warning. It's a rookie mistake that many students make, and I really don't want you to fall into that trap. We are going to talk about lots of different types of energy. We're going to talk about kinetic energy, gravitational potential energy, heat energy, elastic energy, and there will be systems where the energy is transformed from one form into another. For example, we might transfer gravitational potential energy into kinetic energy. When any energy is transferred in a system, the amount of energy that's transferred is equal in numerical terms to the work done on that system. If you have a formula for work done, which you will, we're going to teach you that in a second, and you have some formulas for energy transferred, that makes problems much simpler. So it's really useful for you to pop in your notes now this little phrase here, energy transferred equals work done. I think that will help you as we go through this course. And we'll start with learning objectives 1 and 3. The principle of conservation of energy. Let me tell you, if you learn the principle of conservation by energy off by heart, it often guarantees you 2 marks in an exam. So it's really worth writing this down in your notes. Energy is neither created nor destroyed. It may transform from one type to another. So what we were just talking about earlier, energy transforms from one type to another, work is done in the system, but the total energy of an isolated system remains constant. If you can pop that into your revision notes, I guarantee that will be a very useful definition for you to learn. Let's have a look at Sankey diagrams. What an odd name. I don't know why they're called Sankey diagrams. I don't really want to know why they're called Sankey diagrams. I just think it's a very odd name, and I quite like the fact that I think it's an odd name. Now, what Sankey diagrams do is it's a visual representation of what happens to energy in a system. And they look like a set of arrows. The thicker the arrow, the more energy is in that section. And they're a good representation of the principle of conservation of energy, because all the energy that goes into the system is conserved, but it has different outputs. So it's transferred into different forms, but 100% of the energy that goes in, 100% of the energy comes out. Why do we use Sankey diagrams? Well, to show what type of energy comes out of a system and whether it's useful or whether it's wasted. The input energy goes on the left, as I've shown, and the output energy comes out in different formats on the right. Usually at the top, at the right, is the useful output energy. And usually the arrows that point down are the output energy, but they're wasted. So that's wasted energy. If we look at this Sankey diagram here, we have chemical energy that goes in, the useful energy output is kinetic energy, and the wasted energy is thermal and sound. I suggest that could be a car or a motor. You can look at a Sankey diagram and guess what the system is. In a little break from the norm, we are going to do all of the knowledge questions at the end of this tutorial, and that's because all energy questions tend to be interlinked. It's difficult to get a question based just on a Sankey diagram or just on the principle of conservation of energy. So we'll do all 9 knowledge questions at the end of this tutorial. In the meantime, go to your revision note template and write down the principle of conservation of energy in the definition section and draw and annotate a Sankey diagram in your revision notes. We touched on work done earlier. Let's deep dive into work done by looking at learning objectives 2 and 4. Work is done when a force leads to the movement of an object. So if we check out the man below us, he's dragging a surfboard behind him on the sand. It looks such an idyllic life. He's actually performing work. He's doing work on the surfboard. The fact that work is done when a force leads to the movement of an object, we can kind of surmise that the formula for work done must have something to do with force, and it must have something to do with the movement of an object. And in fact, the definition of work done is work done equals force times distance moved in the direction of the force. Now, you might be tempted to ignore that second line and say definition of work done is work done equals force times distance. You would be very, very wrong to do that. The important part of this definition is distance moved in the direction of the force. And let me explain below. We have two situations here. We have a grey box being moved over a distance S. And when we're looking at work done, we call the distance moved S. The first one is where the force and the distance moved are parallel to each other. And in this case, we can say work done equals force times distance because they're both in the same direction. They're both parallel. But in the second diagram, the force is not parallel to the distance moved. The force is at an angle to the distance moved. So we can't just simply say force times distance because we're looking at the component of force that is parallel to the distance moved. We have to work out the component of force. The component of force in this case, which is parallel to the distance moved, is equal to F cos theta. Our equation becomes force, which is F cos theta, times distance, which is S. Now, if they're parallel, theta is 0 and cos 0 is equal to 1. So if they're parallel, it's just Fs, force times distance. But if they're not parallel, we have to add in this cos theta factor. So we come up with a formula of W equals Fs cos theta. This equation assumes that the constant force is applied. It assumes that this poor man below who's having a terrible time in life, dragging his surfboard along a completely deserted beach. This assumes that he's applying a constant force to that surfboard. Do we think that happens in real life, folks? No, it does not. But we'll talk about that in a second. Now, work done is measured in units of joules, and it is important that you remember the definition of a joule. And we've got it written below. 1 joule of work is done when a force of 1 Newton moves an object through 1 metre in the direction of the force. It's important that you memorise that definition. And actually, it's not that hard because you can just use the formula, force times distance, 1 Newton times 1 metre. It's not hard, okay? So what happens when our force is not constant? What happens if we can't apply the same force to that object as it travels through a distance? I quite like this graph below. I'll give you a chance to look at the axes. On the x-axis, we have the past and the future. And on the y-axis, we have sucking and not sucking. So this poor person's life, well, actually not poor. It looks like in the future he's got quite a good prospects. The future is not going to suck, apparently. And it's going to be the same for you because you're going to pass these IB physics exams with flying colours. Let's get back to work done. We don't have a constant force, okay? So we can't use W equals Fs cos theta because F is always changing. So we have to come up with another way of doing it. And the other way is to use a graph. So the area under a force distance graph, and that's what I've shown here, force is on the y-axis, distance is on the x-axis, is equal to the work done by the object. So if you have a varying force applied to an object as it's being dragged along or pulled along or pushed along, then you can work out the work done on the object by calculating the area under the graph. And we actually have an exam question on that. Let's move on. We've just learned that the area underneath a force distance graph is equal to the work done. This question appeared in a paper 1 for both standard and higher level recently. Let's read through it. A graph shows the variation of force acting on an object moving in a straight line with distance moved by the object. Which area represents the work done on the object during its motion from P to Q? Now, what we'll notice is the force begins with is different from the force at the end. So the force is not constant. That means we can't use W equals Fs cos theta. And in fact, the answer is really given in the question. It says, which area represents the work done moving from P to Q? So we have to calculate the area underneath the line at that point. So the area is y plus z, and that is C. Move on. Here's a weird fact about work done. If the force is perpendicular to the direction of travel, so if the force is being applied upwards, but it's moving along the way, it's perpendicular, then cos 90 is equal to 0. So no work is done. And in fact, if we look at this guy here with the beard and the ponytail, he's carrying a box. He's applying a force upwards on that box. If he moves forward, does a whole lap of the room, he goes anywhere around the room moving forward, then his distance moved is perpendicular to the force that he is applying on the box. So in fact, no work is done on that box by the man. Weird fact, right? No work is done when the force and the distance are perpendicular. And that comes up in exams as well. Let's have a look at the next question. Building on our weird fact about work done, let's have a look at this question here. Again, from paper 1, examined at both higher and standard level. The mass at the end of the pendulum is made to move in a horizontal circle of radius r at a constant speed. So horizontal circle, constant speed. The magnitude of the net force on the mass is F. What is the direction of F and the work done by F? Okay, the direction of F, well, it's a circular motion, and any object that undergoes circular motion experiences an unbalanced force towards the centre of the circle. So the answer has to be A or B. The work done by F, well, F is going towards the centre, and the displacement at any point is parallel to that. Not parallel, come on, is perpendicular to that. So cos 90 equals 0. So our work done is 0. So answer A. A quick, easy way of applying that weird fact on work done. Obviously, we deep dived into work done there, and I gave you a little bit more information than I said I was going to. We talked about force distance graphs and the conditions where no work is done in a system. The reason I've done that is because I've noticed that past papers tend to focus heavily on that when we're looking at work done. So I'm glad we deep dived there. What your job now is to write down the definition of a joule and work done, the equation, draw and annotate a force distance graph, and note the condition for when no work is done in a system. Can you get them into your revision notes now? Let's deep dive into kinetic, gravitational potential energy and elastic potential energy now, and look at how we can use work done and the transfer of those energies to solve exam problems. So let's look at these types of energy, and we'll start with gravitational potential energy. Any mass stores gravitational potential energy if it has the potential to fall. So this guy below us, he's at the edge of a cliff looking down. He has the potential to fall to the bottom of that cliff. So he stores gravitational potential energy. If he'd gone more inland and was standing on a flat surface, he does not have the potential to fall, so he doesn't have gravitational potential energy. So what is becoming clear here is that the amount of gravitational potential energy you have depends on the height that you've chosen as a reference point. Let's look at that in more detail. First of all, the equation, which I hope you're very comfortable with, is that the change in potential energy is equal to mass times gravitational field strength times the change in height. How far is this object changing in height determines how much potential energy is gained or lost. And height is generally defined as the height through which the mass has the potential to fall. So where can it fall to, or where is it falling to? Now, in any given situation or exam question, that will be obvious to you. Here's an interesting thing about gravitational potential energy. The height gained or lost when we're calculating delta H is independent of path. So I'd like you to consider this helter-skelter below. You start at the top, you slide all the way down, having a real fun time, to the bottom. You go on a really, really complex path to get there. But what matters is none of that. Only the top and the bottom matters. What point at the top, what point at the bottom, and that's it. So the object could travel a crazy path, but only the vertical height difference matters. When you're calculating that delta H, calculate only the vertical distance, so up and down distance, between the initial and the final position. Nothing else. It doesn't matter what it does in between. I'd like to link work done by gravity to potential energy, just to give you an interesting insight here. If a body falls a vertical distance, so say I'm holding a ball and I drop that ball, the work done by the object is equal to force times distance. Force, and in this case, force is a gravitational force, and distance is the height fallen. They're both parallel to each other. So we don't need to worry about cosθ in this stage, because cos 0 is equal to 1. So force times distance. Well, a gravitational force is weight, isn't it? So the work done is weight times distance. And the distance is height, so weight times height. And the expression for weight is mass times gravity. So the work done by an object falling a vertical distance is W equals mgh. The work done on an object falling is equal to the energy transferred into or from gravitational potential energy. Similarly, if a ball is thrown upwards a vertical distance, the work done by the object is force times distance, weight times height gained. Because it's in the opposite direction, the force and the height gained are in the opposite direction, we have a minus mgh. So the work done on that object is minus mgh. And in this case, the force is parallel to the direction of travel, unlike the situation where we had the book and they were perpendicular. The next type of energy is kinetic energy. There's nothing hard about kinetic energy. Any moving mass stores kinetic energy. Simple. And the equation is Ek equals a half mv squared. The only tricky thing about this that some people forget about is squaring the v when they're calculating kinetic energy. Always square the v. Sorted. I'd like to think about elastic potential energy now. If you have any form of material, but it's probably easiest to think about elastic bands or a spring or a plastic bag. If you stretch or compress that material, you're doing work on, let's take a spring as an example. If you stretch that spring, you do work on the spring by applying a force over a distance or an extension. And that spring, you might be comfortable thinking about Hooke's law. Hooke's law says that the force you apply to the spring is directly proportional to the extension of the spring. And you might have seen this graph below for a spring. Well, wait a minute, that is a force on the y-axis and distance on the x-axis. Force distance graph. What does the area underneath equal? Well, the area underneath equals the work done. So the work done on a spring that leads to a store in elastic potential energy is equal to the area under this graph. This graph forms a triangle. The area of a triangle is a half fx. A half times the height, f, times the base, x. So the work done, or the elastic potential energy, stored in a spring is equal to half fx. And we remember that because the area under a force distance graph is equal to the work done on the object. Let's take that a little bit further. Any stretched material will store elastic potential energy due to the work done in extending that material. And that's what we talked about in the last slide. If we're looking specifically at something that's undergoing or obeying Hooke's law, we came up with the equation half fx for the elastic potential energy. But F equals kx if it obeys Hooke's law. So instead of popping f into that initial equation, let's pop kx into that equation. Let's substitute the f with kx. And we end up with another equation or expression for elastic potential energy, which is a half kx squared. And that's the expression you'll find in your data booklet. The extension is a measure of how far the material has been extended or compressed. It doesn't have to always be an extension, it can also be a compression, particularly if you're looking at car springs. The final type of energy I'd like to think about today is thermal energy, and that is represented with a Q. When a substance changes temperature, either gains or loses thermal energy. And the equation for that, which you'll find in topic 3 thermal energy, is Q equals mc delta T. M is the mass of the substance, C is the specific heat capacity which you'll be given, and delta T is a change in temperature. And why am I telling you this right now in mechanics? Well, when an object slows by friction, that energy is all transferred into heat energy. So say you have something moving very quickly and friction slows it down, what's actually happening is that kinetic energy is transferring to thermal energy. And that might be a key energy transformation that you'd be examined on. Which brings us into energy transformations. So the most common energy transformation in exams is gravitational to potential. And that's happening here below me on this roller coaster. At the top of this very scary looking dip, the people in this roller coaster have gravitational potential energy. As they travel down to the bottom of this very terrifying looking dip, they gain kinetic energy. So it's transferring from gravitational potential to kinetic. To do questions relating to that, we equate the expressions for two. So mgh is the expression for potential energy, and half mv squared is the expression for kinetic energy. Assuming the mass doesn't change, assuming somebody doesn't jump out of that cart on the way down, then the mass of the object is the same, so we can cancel out the m's on both sides. That gives us g delta h equals a half v squared. Let's take the 2 over, swap it round. And we have an expression here that can be used specifically when things are transferring between kinetic and potential energy. So this expression might be useful where we're looking at things like roller coasters or objects falling under gravity. They start with potential and they end up having kinetic. That's a nice wee exam tip for you. I have a question on here from a past exam paper. Let's go for that. It's a long extended question, and let's go and have a look at this energy transformation. The diagram below shows part of a downhill ski course, which starts at point A, which is 50 metres above the level ground. Point B is 20 metres above the level ground. A skier of mass 65 kilograms starts from rest at point A so that means it's got no kinetic energy. And during the ski course, some of the gravitational potential energy transfers to kinetic energy. From A to B, 24% of the gravitational potential energy is transferred to kinetic energy. Show that the velocity at B is 12 metres per second. So we had to see how much gravitational potential energy is lost. So we're going to use delta EP equals mg delta h. And you remember that this delta h is the vertical distance or the vertical height between the top point and the bottom point. So it makes no difference that it's gone like this in between. We're only interested in the vertical difference between A and B, which is 30 metres. So it starts off at 50, goes down to 20, so it loses the equivalent amount of gravitational potential energy, which is 65 times 9.81 times 30, which comes out at 19129.5. I'm not going to round that just yet because we're in the middle of the calculations. I know that 24% of that is transferred to kinetic energy. So 24% of that is equal to 4591.08. That's how much kinetic energy the skier has at B. We then equate that to the formula for kinetic energy to see what the speed is. So half mv squared. So we'll say v squared equals 2 times 4591.08 divided by 65. And the calculation comes out at v equals 11.88. All of these answers, all of the data is one significant figure, one significant figure, two significant figures. In this case, it's more appropriate to give it to two significant figures, so 12 metres per second, which exactly matches that given on the question. Classic example of one of the most common types of energy transformation questions in paper 2. The next type of common energy transformation is elastic potential to kinetic.
We found previously that the expression for elastic potential is a half kx squared equals a half mv squared if we're looking at this particular transformation. Now, where would that happen? Well, I'm thinking about a spring-loaded gun. I'm thinking about something that's you push into the spring, maybe like a Nerf gun or something. You push a spring down and then you release it, and this Nerf bullet flies off into the air. It starts with elastic potential energy and it ends up as kinetic energy. I think that's my example. And I do have an exam question on this. Let's go. Here's another type of energy transformation question. Again, it was at the very start of paper 2. Let's read it through it. A company designs a spring system for loading ice blocks onto a truck. The ice block is placed in holder H in front of the spring, and an electric motor compresses the spring by pushing H to the left. When the spring is released, the ice block is accelerated towards ramp A, B, C, and when the spring is fully decompressed, the ice block loses contact with the spring at A. The mass of the ice block is 55 kilograms. Assume the surface of the ramp is frictionless and that the masses of the spring and holder are negligible compared to the mass of the ice block. The block arrives at C with a speed of 0.9 meters per second. Show that the elastic energy stored in the spring is 670 joules. So the elastic energy stored in the spring is going to transfer into kinetic energy, because we know that the block is moving at point C, and gravitational potential energy, because it's got the potential to fall. It has moved up a height. So we're looking at the kinetic energy at that point is a half times mass times 0.9 squared, plus gravitational potential energy, which is 55 times 9.81 times 1.2, and that gives us a value of 22.275 plus 647.46, and that is a total of 669.73. We want to take that to two significant figures. We've got 670 joules. The third type of energy transformation I'd like you to be aware of is not of a transformation, but more of a relationship. Kinetic to thermal, and including a bit of work done. When you have a fast-moving object, it has kinetic energy. As you slow it down by friction, either on the brakes or a solid surface friction or drag, work is done on that object to slow it down, and that object's energy transfers into thermal energy. So there's a few different sort of variations of these equations that you could use to calculate a question. So if you're basically looking at a situation where a car is slowing down or something is slowing down, work has been done on the object to change the kinetic energy of the body, and usually it turns into thermal energy through friction. So examples include a car braking and objects slowing by friction. And we have a question on this. Here we have a very simple and quick exam question relating to exactly the transformation we've been talking about. The initial kinetic energy of a block is moving on a The initial kinetic energy of a block moving on a horizontal floor is 48 joules. A constant frictional force is applied, bringing it to rest over a distance of 2 meters. What is the frictional force on the block? So work is being done on the block to change its kinetic energy from this kinetic energy here to 0. So work has been done to do that. W equals Fd. We have Ek totally transfers its energy using work done. So 48 equals force times 2, so F equals 24. The answer is A. Again, I hope you found that useful. Right now, what you've got to do is go to your revision note template and write down the equations for kinetic, gravitational potential, elastic and thermal energy. The best way to get these learning objectives into your head is actually to practice problems. Writing notes down about it wouldn't really make much difference. Let's look at power and efficiency now, learning objectives 7 and 8. We move on to the concept of power. I want you to consider two people. They're both holding this heavy box of the same mass, and they have to get that box to the top of the stairs. One person flies up the stairs in no time at all and gets the box to the top of the stairs. The second person just doesn't have the physical fitness and takes longer. The first person is more powerful because what power is a measure of how quickly work is done on an object. So by flying up the stairs with this box, you're doing work on the object to increase its gravitational potential energy. And if you do it quickly, you're more powerful. If you do it slowly, you're less powerful. The definition of power is the rate at which energy is transferred. So how quickly are you doing work on that object and transferring the energy? The formula that I like to use to calculate power is power equals work done over time. That's not in the data booklet. So if I were you, I'd memorise that formula. It does have units. It has a unit of watt. And if you're watching really lame videos on YouTube and stuff, then somebody will joke and say, ha ha ha, I've got a question for you. What is the unit of power? And then they'll say, I don't know, or it's a watt. You go, I answered it already. It's just awful. Anyway, 1 watt is equal to 1 joule per second, and that is a definition worth knowing. An exam tip for you. If an exam question asks you to find the rate of energy transferred, it means find the power, because finding the rate of something means dividing it by time. So if you're to find the rate of work done or the rate of energy transferred, it means work done divided by time or energy divided by time, which is power. There's another expression for power, which you do find in the data booklet, unlike the last one. Work done equals force times distance, right? So power equals work done over time, which equals force times distance over time. Now, if the force is constant, we can take the force to the front, and we can say power equals force times distance over time. What's distance over time? You got it. It's speed or velocity. We have power equals force times velocity, or power equals force times speed if it's going in one direction. That is in the data booklet, and it's useful for when you're looking at objects travelling at speed. Finally, we're on to the concept of efficiency, and I have an exam tip for you. Efficiency is usually found in transformer and electricity questions. It's less common in mechanics. So whilst that's not a guarantee, it's more likely you're going to talk about electric motors or transformers when you're looking at efficiency. Most mechanical objects, like the one we have below, this wind turbine, or an engine and so on, have moving parts. So things have to rub against each other for stuff to work. Imagine gears, ball bearings, all sorts of stuff working within a wind turbine or an engine. As soon as anything moves against another thing, it creates friction. So that means as soon as we have friction, energy is being lost and wasted, so the efficiency is decreased. Mechanical objects tend to be quite inefficient, down at about 30%, some of them. When you have a transformer, all that's moving in a transformer is an alternating magnetic field, which is not a mechanical concept, it's an invisible field. Nothing actually moves in a transformer. It sometimes can heat up, so a little bit of energy will be lost to heat. But in general, a transformer tends to be highly efficient. You can get transformers up to 95% efficient. When we're talking about efficiency, it's usually represented as a percentage. And I'll be honest with you, it's not very hard. Use the formula below. They're in the data booklet. There's not much else about it. Power and efficiency problems tend to be lumped in with energy problems, work done problems. So it's very difficult for me to put out specific problems about power and efficiency on their own. What you'll also find is the actual maths tends to be quite complicated. So it's maybe something to do with generators and they're only 30% efficient, but there's 5 generators, and you'll have to really read these problems. And we'll do some practice problems at the end of this tutorial to allow you to practice problems on power and efficiency. But in the meantime, go to your revision note template, write down the definition of power and efficiency, and write down the equations for both as well. Finally, our learning objective 9 is about energy density of a fuel source. When we're talking about fuel source, I'm talking about things like coal or oil.
And there's a very good reason that you might choose coal to generate electricity over oil, and that's because of the energy density. The energy density is basically a measure of how much energy you can get out of a particular substance. And there's two types of energy density. Specific energy density is defined as the energy per unit mass of a fuel. So if you have 1 kilogram of coal, how much heat energy can we get out of that? And the energy density, which looks very much like the specific energy density, I get that, is defined as the energy per unit volume of a fuel. So if we were to look at it on the coal, it's like how much energy can we get out of 1 cubic metre of coal? You can see that specific energy density refers to mass and energy density refers to volume. And it's important that you understand the difference between those two. Again, when you're looking at problems on these two concepts, it really is common sense and a bit of maths. There's really nothing else I can teach you here without you just going and practicing the problems. And now you're allowed to practice the problems because we have reached the end of Master the Majority in Work, Energy and Power. I've taught you all the concepts. Before we go to the knowledge questions and complete questions 1 to 9, just quickly go to your revision notes and write down the definition of specific energy density and energy density. As a final note here, you will find these knowledge questions hard. Don't worry, the knowledge questions are designed to really test every single little element of the course.